Hello Year 13 chemists, welcome to TP's Chemistry Cuts. In this clip we carry out a series of calculations on a strong acid, strong base titration curve.
Okay. First thing we need to get our heads around is that pH is a logarithmic scale. Remember, we use a logarithmic scale because it's a huge range of values and we need to compress it into something that's usable. And so it's not linear. So when you change one pH, you're not basically removing equal amounts of acid or base when you're carrying out a neutralization. Logarithmic means that for each pH, and I've put this on the board as a simple exercise, remember the concentration of H3O plus is 10 to the minus. So you're going from 10 to the minus 1 to 10 to the minus 2 to 10 to the minus 3. So in other words, the concentration is 10 times less for each pH value. So it's a factor of dilution, if you like, where you're going to 10 times less the concentration, but you're only moving one pH value each time. Okay? Once you've got your head around that, it means that when you're carrying out an acid-base titration, you add equal amounts step by step. You're removing equal amounts of whatever it is you're neutralizing. So when you remove equal amounts, you're not changing the concentration by a factor of 10 every time you remove equal amounts. You're basically changing it in a linear way, the concentration. But that doesn't mean that the pH will change linearly. Okay? Does that make sense? So that's something to start off with. That's why we don't, when you do a neutralization reaction and you plot the pH versus the concentration or the amount of acid that you're adding or base you're adding to whatever is being neutralized, you don't see a nice straight line. What you get is a curve. This is a typical curve you get when you add a strong acid to a strong base. Okay? And I'm not going to go through the reverse where you add a strong base to a strong acid because it's literally just a mirror or an inversion of this. So rather than going like this, it goes in the opposite sense, if you like. And you can see there's a number of features. Okay. First of all, you start off with a low pH value, okay, because you're starting off with a strong acid. And the first thing to notice is that as you're adding base to it, the pH isn't changing very much. Okay. So it could be, if you start with a 0.1 mole per litre solution, you've got to add a lot of acid until you get to 10 to the minus 2, 0.01 mole, and that's going to be when you get one pH change. So you're almost here. So that's gone from 0.1 to 0.01, and that accentuates the non-linear nature of this, okay? And then suddenly, with small additions, you get enormous change in pH. Okay? And at this point, here in the middle of this very steep curve, what you've done is added a mole equivalent of, in this case, strong base has been added to the strong acid, and so this is what we call the equivalence point. So you've exactly neutralized away your strong acid with the exact amount of strong base. So that's the first thing you need to label on there. Okay? And then beyond here, you're adding more and more base, so you're just getting a gradual increase in pH, but it's getting closer and closer to a particular point. And that will be the pH of the base you're adding. It'll get closer and closer to it, but never quite get there because of the dilution effect of adding base to an acid. You're adding two solutions together, you're getting an increase in volume. So the pH of the base in this case would be 13, but you're getting closer and closer to it. Okay? So here we have acid only. Okay? At this point, we've got salt only. Okay? So this would be NaCl, for example. I won't put it in, but if you're taking sodium hydroxide and adding that to hydrochloric acid, all you'd have in solution would be sodium chloride solution. And then here, this is base plus salt. But the pH whereas so the pH up here is caused entirely by the excess base you've added, because you've gone past equivalence, you're continuing to add base, and so you've got excess base, and so the pH, the high pH, is being caused by the excess added base. That's the thing to remember. Okay? So why don't we label that? Now, because we're adding a strong base to a strong acid, in the neutralization reaction, which we've put the equation for there, we're forming the conjugate base of the strong acid and the conjugate acid of the strong base. What can we say about both of those two conjugates? Because they're coming from strong acid and a strong base. What can we say about the conjugates? Think about them. We're forming sodium chloride if we add HCl to sodium hydroxide. What can you say about sodium plus, which is the conjugate acid of the strong base? And what can you say about Cl minus, which is the conjugate base of the strong acid? Unreactive. They're both unreactive. Okay? So, what does that tell you about the pH at the equivalence point? If neither of them is going to react with water, okay, so nothing is going to be interfering with water. The only thing that's going to be causing the pH is water itself. What's the pH of just water? 7. Okay, so the midpoint there of that steep curve, the equivalence point for a strong acid added to a strong base, or the opposite, a strong base added to a strong acid, will always be 7. For any curve for a strong acid, strong base, this steep bit here goes to +4 or -4 pH points of the equivalence point. So when you're coming to plot a curve, you don't need to calculate everything on the curve, you just need to calculate a small number of points. This is one that you know is going to be pH 7. You know that that steep bit is going to be basically 8 pH points. So in other words, just adding 1 or 2 drops of, in this case, base, causes the pH to change by 8. So in other words, 8 more orders of magnitude, the concentration of OH basically is increasing by 8 more orders of magnitude, or the concentration of H3O plus is decreasing by 8 orders of magnitude. Now, in addition to that, we can calculate several points, or three points, or 2 other points. We can calculate the pH here. And because this is a strong acid, which completely dissociates in water, then this is just minus the log times the concentration of the acid, okay, because it's a strong acid. So whatever you're given as the concentration of acid, you use for the kind of calculation of pH, so you can do that quite easily. We already know that this value at the equivalence point is going to be 7. Okay, so here we've got pH equals 7. The other thing is, although I've assumed here that the concentrations are equal, they may not necessarily be equal, and it's a trivial matter to work out what the volume is at the equivalence point. Okay, you don't need it for this particular titration, but you will need it when you come to any titration that involves a weak acid or a weak base. Okay, so we can work that out. It's very straightforward. We won't do it for this to say because we don't need it. The other thing is we can work out the pH here. Okay. Now, this volume, when we get to the equivalence point, is basically just water when we're considering what's affecting the pH. What we've done is we've created a salt which is the conjugate acid of a strong base and the conjugate base of a weak acid, strong acid, neither of which are reactive. So the pH at that point is due to the water, which is why it's 7. So basically what we've got there is a volume of water, okay, that's causing the pH. What we're doing is we're adding base beyond that, strong base. So the pH is due to that strong base, but we get a dilution effect caused by the water that we have in the solution that we've mixed up to the point where we've got equivalence. Does that make sense? So we get to equivalence and we've got a volume of water in there, and then we're just adding base into it. So it's a dilution effect. So what we need to calculate this pH is the concentration of OH minus that's been added in excess, and then we have to work out the diluted concentration due to this extra water that's been added into. Yeah? So so we'll come back and do some calculations involving this later. But that's the important thing to understand. So here, it's a strong acid, complete dissociation. We can calculate the pH due to that acid by assuming it completely dissociates. The concentration of the acid is equal to the concentration of H3O+, so we get the pH. We know, or you can calculate the volume at equivalence. Very straightforward thing to do. And we know that the pH is going to be 7 there. We can draw in a steep line going plus or minus 4, and then it's a case of you can round that off and draw a line going down to this cross. You can calculate the pH if you know how much base you've added here, and then you can divide that by the total volume of water that's in the flask due to the initial acid volume, the base added to get to neutralization, plus the volume added beyond neutralization, and that will give you the pH, that will give you the concentration of OH minus in the flask at this point, and then you can divide that by, you can use that to calculate the pH. So you can then draw a curve and draw it up there. So these things are actually quite straightforward with a little bit of practice.